get everybody together is to have exactly that conversation.
It's been my experience that trying to maintain multiple versions of a code is very difficult. I'd much rather maintain a version with switches in it to switch between capabilities, which is what KRC is. It's got a lot of switches. And the whole question of the future is it's up for grabs. Where are we? Okay, we've got a climate model. I happen to use one I derived from Mike Smith's tables, which he sent me. Josh probably has a different one for the generic Mars year. That's what it is. It's a generic Mars year made by averaging those years that we've measured and interpolating smoothly through the blanks. You could put in your own. If you want to change the spacing in latitude and LSB, then there's a couple firm-coded numbers that would need to be modified. The other thing it does is it allows twilight. I don't know of any models that do this at the moment. But Mars does have twilight. If you read the literature carefully, you'll see images taken in twilight. And so this model allows twilight by a somewhat hokey method of just taking the day and geometrically spreading it a little bit longer. But it's in there. And normally I run with twilight set to 0, just because it's cleaner. The way the model handles twilight is a little strange in that the energy gets to the surface, but the atmosphere doesn't absorb any during twilight. In other words, there's no absorption of solar energy into the atmosphere in that twilight period. Sun's almost set anyway, so it's probably not a big deal, but it's just not there. What's next? Okay, beginning to get into the surface condition is radiative balance above, thermal diffusion below. So you specify the albedo, which is the reflection coefficient for solar radiation. Spectrally balanced, it's whatever the average is across its actual spectrum. What fraction of the solar energy is absorbed by the surface. And it assumes that that is the same no matter what direction the sun is shining upon it. I mean, it's called a Lambertian surface. So in fact, the fraction depends on the projected profile, the cosine of the incidence angle. But the photometry is called Lambertian. That is, its apparent ability to absorb energy is the same in all directions. Has a thermal emissivity. What fraction of the black body temperature does it radiate? And that is temperature independent at the moment. And it has a slope and an azimuth, which we'll get back to. The frost can have a different albedo and emissivity than the dry soil. In fact, I highly recommend that you do. And the frost albedo can be the fundamental value. I mean, there's always this variation with thickness. As it gets thin, it gets less effective, no matter, and you can, well, actually, again, more parameters. You can turn that off too, if you want to, but normally it gets less effective. In addition, something peculiar happens on Mars which is still awaiting explanation. We've observed it, but we don't know why. The brightness of the snow depends on how bright the sun is. It's not how bright it is, but what fraction of energy it reflects. The more sunlight you put on Mars, the brighter the frost gets. Now, nobody knows why. It's just what it does. And that's coded in here based on a paper by the values. The default values are based on a paper by Dave Page 20 years ago. But you can put them to be whatever you want. Or not. Pardon?
I mean, isn't that just the same thing as saying that there's a phase function of
No. Not, well, we don't know the answer to that.
Okay, but that's a possible explanation.
Yes, in fact, we should ask Dave, but we'll go back and read the paper. The problem is the observations are very limited in phase coverage.
Sure.
They may be, there could be CMUS observations that we've never, or TESS observations that nobody's ever gone back and looked for this. But they could be there.
Almost certainly TESS has those observations with all the EPS we did.
So,
Can I interject again here? We're in a mode with Odyssey and Themis where we're under a lot of pressure to do new stuff. I mean, a ridiculous amount of pressure to do new stuff.
As long as it isn't new, though. That's
Well, even that, now that MSL is safely on the ground, we're kind of allowed to
do things
do
again.
things as long as they don't stress the broken reaction wheels or whatever. So anyway, for example, one of the things I've proposed is letting the orbit, instead of, it's drifting back because the spacecraft wants to be near the terminator. It's just so much safer to run it there. Great. But it can be 1 hour before the sun sets, or it can be 1 hour after the sun sets. And so you could actually let it drift around and be making morning observations. So things like phase functions and polar caps, and if there's things data we haven't been collecting, that we should be collecting. Doing rotos is going to be tricky, but local time, we might have some flexibility. So if there's some of these things that, gee, we ought to investigate that phenomenon, the next year is the time to be thinking about it.
Side issue. Did anybody ever look for specular reflection over the polar caps? And was it there? Oh, shucks.
We actually did that with TESS.
Okay.
One of the early things we did with TESS. We
Okay.
actually figured out exactly the specular point.
Okay. Wasn't over cryptic terrain, was it, when you did
God
that?
only knows. It was the thing about orbit, this was probably 1999.
Somebody else knows. Okay, well, it'd be great to do it over cryptic terrain, but of course you don't know what the surface is doing and all that. Okay. The imbalance between the solar and thermal radiation goes into changing the temperature of the top layer. Standard thermal diffusion equations. Or changes into the frost amount, one or the other, depends on whether there's frost there. And an aside, I'm going to mention a couple of books based for those people who really feel sadistic. There's a book called Heat Diffusion, something like that, by Karslaw and Jaeger. It's a classic Oxford tome on heat diffusion, and all the answers are there someplace if you could ever get through the book. It's really a heavy-duty book on this stuff. Okay, the subsurface is simple thermal diffusion based on that little 3-point to 1-point scheme I showed earlier. So you just have to specify these things every place. We've talked about the lower boundary. And again, you can have two materials, one for a certain number of layers and another for another number of layers. And that probably also represents Mars. And this is where this instability becomes important. You'd love to have a really thin top layer, but if you want to do that, you got to have really rapid time steps. KRC isn't set up to do that. Okay, here's the atmosphere and the multiple scattering. So it's gray, spectrally gray. That means I don't give any account of wavelength dependence. I assume whatever the coefficients are, they're the same at all wavelengths. But those numbers can be different in the solar and the thermal regions. So it transmits, absorbs, and scatters solar radiation using a two-stream delta Eddington, which we'll get into in a moment. And it transmits, absorbs, and emits thermal radiation isotropically. The flux imbalance goes into changing its temperature. Over mass of it is, you have to assign things like, pressure. You have to convert pressure to mass and assign a specific heat for the atmosphere, blah, blah, blah. Straightforward stuff. And I'm saying that dust amount and radiative characteristics, they can be specified. The direct sunlight, the surface is Lambertian, as I also mentioned that. And there are three terms. These are actually the names of the variables in the thermal radiation part of this, the visible radiation part. Direct is the sunlight that hits directly on the surface. There's diffuse radiation, it's the skylight that's coming from the bright atmosphere. When you look outside and look at the blue sky, that's diffuse radiation. When you look straight at the sun, don't do it, that's direct. And when you look at a building, you're looking at bounce. Okay, so that's all. So it handles these three things separately, and the reason it has to separate them is because you have to consider two kinds of surfaces more or less simultaneously, a flat surface and a slope surface. All of these are normalized to the total incident flux at the outside of the atmosphere, which is called SOLR, and that number is simply the solar constant divided by the square of the distance from the sun. Standard heliocentric stuff. And we'll look at some of the equations that this gets a little involved for sloped surfaces and craters. The surface pressure I've already mentioned, it can be any one of these three. The global integration of the amount of frost requires that you actually calculate what the poles are. Now the program's not smart enough to go look and see, well, how many did he do in the North Pole, how many did he do in the South Pole? It just tests, did he do at least 8 latitudes? If you've done at least 8 latitudes, it'll allow you to do this integration. The integration will be based on the actual latitude you did. And so if you try to do this without actually doing any polar latitudes, something weird is going to happen, I don't know what. Normally, well, you see, okay, two-stream delta Eddington. This is named for Eddington, who was an early, sort of maybe the first radiative transfer scientist. And the two-stream means it actually breaks the radiation into two components, a direct component and a diffuse component. So those are the only two streams. When they talk about 4-stream or 8-stream, it's basically not only do we have a direct component, but we break the diffuse component into angular sectors to more accurately represent what's really going on. This one, all those angles are all just one. There's a reference to the paper that described this. If you look in the code for this delta Eddington subroutine, you'll see more references which are based where I actually got the equations, which was some work by Whiscombe and some other people who actually cleaned it out. So here's the name of the routine. You can see the citations therein. And the comments therein tie the equations back to the original articles. The scattering uses the Hennier-Greenstein, oops, there should be an N there. Sorry, Greenstein. I actually knew the guy. The asymmetry is set by what's called the Hennier-Greenstein G factor. And basically, it's the following. If you imagine light hits a particle, it gets scattered. It could get scattered in all directions. And then the Hennier-Greenstein parameter is 0. There's no preference for forward or backward. It goes in all directions. As this parameter goes toward +1, the scattering becomes low bait and more of it goes forward. If it gets to be -1, the scattering, more of it goes backward. In every case, it's a nice, see if I could draw this. Let's imagine that 0 is the center. So for isotropic radiation, it goes like that. And if it's +1, it would go like this. Or near if it's plus, if it's negative, it would go back this direction where the light's coming this way. And that's what real particles do. Small particles down toward the wavelength of light. Basically, small particles tend to scatter anisotropically. And so that's the way scattering is handled here. And you can set the single scattering albedo, which is what fraction of light that hits the geometric cross-section gets scattered someplace or other versus absorbed. It's called the single scattering albedo, and the maximum I allow is 999, which is could be a limit for really good scattering particles, but that's and there's, I set that limit, for those of you who are interested in this, when I was still trying to do this in single precision. I found out for this part of the program, and only this part of KRC, you really need double precision. Because real scattering parameters do get up to this kind of value. That is, particles get to where they don't absorb anything. They just scatter almost everything. And when you get into that regime, you have to use double precision to actually solve the equations. You had a question?
What is the default value for that?
I don't recall, but we'll see it. Okay. Dun, da, 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 da. Surface thermal inertia, specific density, determined conductivity. Okay, for the surface layer, you actually don't input the conductivity. You input the thermal inertia, which is the number you care about typically, the density and the specific heat, and it calculates the conductivity. For the bottom layers, you actually put in the conductivity, the density, and the specific heat. It's an oddity left over from the way this thing evolved. The first layer is 0.18 of the diurnal skin depth. That's what DSD stands for. And successive layers are thicker by a factor of 1.2. This is the essence of the treachery and trickery of KRC. The fact that it uses layers that are not uniform, but increase in geometrically as you go deeper and deeper, because that's the nature of heat diffusion. The time resolution mellows out as you go deeper into the material. If you ever tried holding a match up to a rock, it doesn't do much. Hold a match up to a piece of paper, bingo, thermal inertia is low. So time scales are important, and heat time scales that decrease as you get deeper into a material. If a layer becomes so thick that thermal diffusion through them is small in a given amount of time, I mean, it's always, there's some non-zero amount, but it's relatively small. If it gets to be small, I make the layers thicker by doubling them. And I'm sorry, not doubling them, back off. If the heat diffusion is small, I double the time step. So this thing has geometrically increasing layers downward and time steps getting bigger and bigger and bigger as you go inside. That is the fundamental nature of KRC. And at the time I developed this, which was, a long time ago, I don't know if it was common practice or not. I don't know if anybody else had done it at the time. I just worked it out and did it. And because it represents the physics. And I cared a lot about how long the computer program took to run. And elaborate startup and convergence techniques and stability tests. I don't really plan to go into these. If you want to, we can. We'll actually bring up the code and try to work our way through them. Most of this, the outside view of the convergence tests is described in the paper. The inside view is in the code. That's the only place. It would take more time to write it up than it would be to understand the code. But basically, KRC runs we'll get to it. We'll get back to it. Ask me about convergence when we get to the daytime, one day after another part of this. The reason this scheme allows practical treatment for both the diurnal and the seasonal heat flow, which have timescales differing by a factor of 680.
So if you, the only, I mean, I agree. I think it's well beyond the discussion here, but that the thickness of the first layer, I mean, if people really wanted to start looking at what if I had a millimeter of dust sitting on a rock, what is that doing? I mean, that's a fundamental limitation. Well, how hard would it be to go back and make that 0.18 something different?
No trouble at all. It's an input parameter.
But would I mean, if I change that to 0.018 by a factor of 10, made that first layer a factor
Okay.
of 10 thinner.
Stay tuned for the stability criteria.
Okay.
But the answer is now, make it anything you like. In fact, KRC is probably smart enough that if you set something wild here, it'll catch it. It may catch it during the early setup phase. If it doesn't, it'll blow up and say, I give up.
Okay. So it's. Right.
Yep.
We'll come back to it.
It's an input
I'm assuming
parameter.
it runs a factor of 10 or 100 slower, but so what?
Yep. You can do a lot of things, and I have not pushed the envelope in all the possible dimensions. 127 input parameters, an enormous number, and I've just pushed one at a time, various times to see what I can do.
So is this 0.18 skin depth that you've chosen one of the input parameters that you selected all those years back, just after sort of careful
Yep.
trial and error? And
Yep, it is.
Was it selected on the basis of computer speed and memory size? Or is it based, I mean, is there something that's...
It's my memory size is now the problem.
Well, I can imagine back in 1969, sure, I would have made it. But
You were there, in fact, almost. I mean, not quite, but.
Yeah, well, I think some of us are very interested in the physics of what might be going on. Like, for example,
Okay.
these beautiful ripples that all the rovers have seen. You drive across a sand ripple, and you disturb it with a wheel, and the upper surface has these millimeter granules, and right beneath it is sand.
Okay.
Oh, hey, can KRC model that?
The answer is possibly, but not easily. What we'd probably want to do is go to a Crank-Nicholson scheme, go to a different scheme. There are ways to solve the numerical heat diffusion equation which have no stability limits. They're stable for all kinds of thicknesses and times. They are more complicated than this. Virtually all of them require solving a matrix at every time step at every layer. So they're way slower. But with modern computers, there's no reason these days to not do that, and there are groups that have done that. I don't know, the group in Germany, Hilbert and company, may have done exactly this. I don't know what scheme they use. But I make a guess it's not something that would be easy to accommodate in KRC. As we get deeper into this, you'll see why.
So you mentioned that there are two types of layers? Or
There are two kinds of material. This is terminology only.
this was the case like that.
Yeah, KRC has a set of layers that get thicker and thicker and thicker as you go down. Now, what I didn't tell you is that thickness, this DSD, diurnal skin depth, is a key concept to this whole business. Diurnal skin depth is the distance at which a daily change in temperature at the surface is attenuated by a factor of 1/E as you go deeper into the material. Fundamentally, that's what skin depth is. All you scientists have come across skin depth, certainly. It's like scale height. It's the distance over which things change by a factor of E. In this case, it's the things at which have a time scale of 1 day, however long your day is, 1 solar day, get attenuated by 1/E. And all of KRC works actually is scaled in those parameters. So anyway, okay, I'm going to try to answer all your questions. First, there is a switch in KRC that allows the layer scheme to be based on the diurnal skin depth of the top material, whatever it is, could be uniform all the way to the bottom, or the layering physical in meters system changes when you discontinuously change from top material to lower material. The thickness of the layer scheme adopts that and is scaled to the local diurnal skin depth, even though it could be well inside the material. And that's actually the safer way to run this program, where the layering scheme, the layering thickness in terms of its local diurnal skin depth, its local diffusivity, actually. The layers are scaled to the local diffusivity, or they can be scaled every place to the top diffusivity. And you ask how many layers can there be? At the moment, I think 30. KRC has 2 virtual layers. Layer Fortran index 1, C index 0, the top layer, is a virtual layer. It doesn't exist. The surface is between layer 1 and layer 2. Layer 1 is put in because it makes the equation set a lot easier. The layer 1 is set in, and at each time step I give it a temperature such that when I treat it like a layer, it generates the right heat flow at the surface. That's layer 1. All the way at the bottom, if you specify 20 layers, there is actually a 21st layer which you don't see. And its properties depend on how you set the lower boundary condition. If you set the lower boundary condition to be isothermal, it's an infinitely thick layer and it has a fixed temperature and it conducts through that surface. If you set the lower boundary condition to be adiabatic, no heat flow, when it gets to that layer, it just gives it the same temperature as the layer above it. And therefore, there's no heat flow. So it's a technique that makes the equations you have to solve in the innermost time loop the simplest.
Does the diurnal skin depth change dynamically throughout a model? So say as the thickness of your polar cap is increasing, does the thickness of your layers change to accommodate that thickness?
No. That is an approximation of the system. The layering scheme is set up at the beginning of a run. If you have temperature independent properties, that's what it uses. If you have temperature dependent properties, it assumes the temperature will be 220 Kelvin and uses those values to calculate the physical numbers that go into the diurnal skin depth and sets up the layering scheme. So the layering scheme is based on a temperature of 220 Kelvin, which is near the middle for Mars. If we're going to do something, and I've forgotten exactly how firm coded that is. It's probably firm coded someplace. And so if we were going to solve, if we were going to do Kepler 4, which is, you know, if you're going to do Mercury, you'd probably want to change that number. But that's a relatively, that would be easy thing to change. Who's keeping notes? Who's the secretary?
The guy in the corner with the video camera.
Recording.
Well, no, I'm just saying.
No, it would be a good idea. It would be a good idea to, okay, I'll make a note.
I think we're all hopefully taking notes. No one's been assigned the formal task of writing down.
Okay, I'm going to write this one down. And let's see. What do you want to do?
Recording these slides as well somewhere else besides the video camera?
We have the slides.
Okay.
Actually, you don't, but you will. This is different than it was 3 days ago.
We'll get that.
So what's the issue here? What is it you really want?
For what?
This thing we've been discussing about how to change the layers.
For me, it would be,
Okay, so it's the
is there
default.
a way to have more layers, thinner layers? You know, what are the limitations? You said it was hard, but what if I just made all the arrays so that instead of 31 layers, they were all dimensioned by 100?
Yeah.
I divided that thing instead of 0.18, I made it 0.018, and I let KRC run, and I come back and
Okay. The answer is it probably could be done easily, and there's some tools that would help you do that. I think, I'm not sure of this, I think you can set these numbers the way you want them and tell KRC to go, and it will calculate the layer table for you before it quits due to numerical instability. On the other hand, there are some checks in there, and it might modify the layer table to try to keep it stable. And I'm not sure which. The easy thing to do is run it, because as you know, a KRC run takes less than a second, typical run. So the easy thing to do is to try it and see if it blows up. KRC will blow up and tell you if it blew up, and it'll tell you right where it was. So, I mean, in general, you can do that. There's no reason. Bits are ephemeral. Run it any way you like. Just don't trust the answers without thinking about it.
Although, go ahead.
Well, the other one was, can you change the thermal skin depth dynamically as your surface properties are changing the same
Yeah.
process condensing on the surface? But I would also ask the thermal polar cap expert in the front of the room, haven't already done this, is it even necessary?
Well, the first question is, it would not be easy to do, because as you'll see when we get into this, the layers, the way, in order to run quickly, remember, I did everything I possibly could outside the innermost loops because I wanted this thing to run fast. It was a matter, if it had been slower by a factor 10, it would have taken a whole university's computers for half a day. You know, I couldn't do that. So I put everything I could by hand. I mean, the code was hand optimized rather than some modern compilers will try to do this kind of stuff for you, and I don't know how good a job they do. But this thing was hand optimized, and I doubt that any modern compiler can approach it for the efficiency that it has. But there are costs, and one of the costs is a loss of flexibility for what happens in detail there. It's probably not necessary. First, because the temperatures, when the polar cap forms, the temperatures just go cold and they just stay there. Nothing really extraordinary happens. And I'll actually show you a properties table for some arbitrary minerals that it's not a big effect. Let's go on. Any more at this point? Yeah.
I just had a question to clarify, and this may not be important. I'm just curious. You were talking about the working with two layers and how the different diffusivities will affect the skin depth.
Two materials.
Two materials, yeah. That will affect the skin depth that you're using. So before you reach the second material, are the layer thicknesses defined based on a skin depth using just layer or material one's sensitivity? So,
yes.
And then once you reach the next material, the skin depth definition changes?
It can or cannot. There's a switch.
Okay.
You may or may not.
But it continues increasing at the same factor rate?
The thing that is constant, whether or not you set the switch, is in terms of one way to run is the layer, you calculate the diurnal skin depth, you set the top layer based on whatever this 0.18 is, everything's thicker by 0.12, all the way to the bottom of the model. Done. Whether or not the lower layers have different materials. The version 2, which is the way I recommend, is when it gets to that boundary, it recomputes the scale of the diurnal skin depth, uses this whatever would be the factor. So suppose it's down 5 layers, so it's 0.18 times 1.2 raised to the 5th power, that product. It takes that value, multiplies it by the physical diurnal skin depth to set the actual layer, thickness of the layer, and then uses that ratio on down. Here's a cartoon from some earlier test presentation. This is the essence of the model. Boundary conditions, sunlight, and planetary radiation. Those are the 2 boundary conditions at the top of the atmosphere. Delta Eddington occurs over here, isotropic occurs over here, different opacities. And that tells how much radiation gets to the bottom. The atmosphere can be dusty. It can vary with season and elevation. The pressure can. The dust can vary with season. There is no conduction to the atmosphere. There's no thermal connectivity between the atmosphere and the surface. It's only radiative connectivity. And then the surface can be the flat stuff, or it can be a slope. And by a slope, you have to imagine a slope as just being, goes forever in both directions. Doesn't have a bottom, doesn't have a top. It's only angular geometry. That's what a slope is in KRC. That slope, however, can look out at a horizon and see the brightness and temperature of the plane extending in front of it. And the top of the slope realizes it doesn't have 2 pi sky, doesn't have a hemisphere sky. It has a fraction of that it's going to get diffuse radiation from. And then a pit makes sort of the same assumptions, except the primary thing that goes on a pit is the sky gets more and more constrained. And frost can form, and if it frosts, it sits right on the surface, right here at the virtual layer. There's no thickness implication. It's all magic mass right at the virtual layer. Then you can have 2 kinds of soils, and this is probably representative of Mars. You can have a dry soil with a thermal inertia on the order of 200 SI units. And below that, you may have icy soil whose thermal inertia is about an order of magnitude higher. And so it really sort of locks the temperatures in more. And at the very bottom, you can have insulating or constant temperature. And you have the option for temperature-dependent conductivity and heat. It's a switch you turn on. Either all the layers or none of the layers are temperature-dependent. So in a sense, this is the cartoon. This is what it does.
The only thing I'd add to that, which I think is relevant to many people in the room, is icy soil / bedrock.
Yeah.
Right.
It's defined by KRC.
Right.
Yeah.
But I mean, bedrock is essentially the same thermal inertia.
Okay.
So people are using it
Yeah.
actually for buried bedrock as well as ice.
The thing I haven't mentioned, and actually there's no place in these slides except maybe 2 words some places. Suppose you have lateral heterogeneity. You got exposed bedrock here, and you got a sand dune here. You got a granule lag deposit over here. And you look down with something that's got 3-kilometer resolution, what do you see? Well, the easy way to handle that, the way KRC handles that, is you run each of the models independently, and you add them in proportion to you think their fractional coverage is. That's an approximation to this thing. KRC has no lateral heat transfer. It doesn't look sideways to see what its neighbors are doing. Yes? I hope.
Why you assume no conduction
To-
of that?
Here? Short answer is simplicity. The long answer is, what kind would you like me to put in? What's the wind speed? What's the surface roughness? Okay, I'm sorry, I don't know your background, so I don't know if those are recognized as sarcastic questions. The problem is...
John's English has improved dramatically,
Okay.
including his understanding of American humor and sarcasm.
There's 2 reasons. One is simplicity. I just don't have to deal with it. The second reason is it introduces a lot of physics which are variable from place to place on Mars. The conductive coupling, I could put in pure still air, no motion, conductivity between a flat plate of steel surface and a gas. There are equations for that allow you to do that. It's a very small term. What Mars actually does is the wind blows. And the amount of heat transfer between a surface and the atmosphere depends upon 2 primary parameters. One is the roughness of the surface. If it's perfectly smooth or if it's got rocks and cobbles and trees on it, and the wind speed. And so now I have a situation where I have to introduce two more physical parameters. And so that's where my satirical question came. What roughness do you want me to use? What wind speed do you want me to use? I mean, I could put those in as parameters, and actually probably not that complicated to do. I haven't done it. If you put them in, the next question is the roughness probably of the surface would be the same all day long, but the wind speed surely would not. Like most planets with atmospheres, the wind speed is a pretty strong function of time of day, particularly if there's any topography around. And the variation with time of day depends a lot on what's happening around you. It's very different between a flat plain in the middle of Kansas in America or the slope of a steep mountain. What happens through the day is very different. So all of a sudden I've introduced a lot of complexity. And they are complexities which in general I don't know well enough. So I made the default decision by not even thinking about it to not put that stuff in. It could be put in. You have to recognize the magnitude of the complexity. Sadat.
The question is, I mean, yes, it's easy to just ignore them, but how much will this, for example, the wind affect the result? The only issue I worry about is if you ignore them, will them really affect
It's a very good concern. And in fact, as I sort of mentioned earlier, it can have a significant effect. And there is one group, and I would have to look up the paper, within the last year, this has appeared in the literature, that the magnitude of the winds in the afternoon could be generating some of the temperature variations we see on Mars. KRC currently does not handle that. But it's now known to possibly be a significant effect.
So for globally view, KRC is good enough. I mean, for some very locally place, it's not that good, right? Does that mean?
I would not make that statement. But as you'll see later, KRC, except for the pressure being a function of polar cap mass, KRC runs one place at a time. It knows nothing about the rest of the planet at any instant. It may look like a run that covers the whole planet and all year to you, but deep inside, KRC only knows about here and now. I know about this vertical column of soil. I know about this atmosphere directly above me. I know nothing else at all. And it's important to remember that. It's fundamental to the way it's written. Deep inside, KRC is only one place at one season.
I think another answer to the question goes back to the afternoon cooling. And what IRTM showed, which sadly was the last instrument that had real diurnal coverage, the pre-dawn temperatures, the noontime temperatures, up to 2 p.m., those temperatures fit pretty well with what the thermal model was predicting. There was this unusual afternoon cooling. But even by 5 p.m., the temperatures had sort of come back to what the model was predicting. Right. And so
Sorry, Robin?
So, right. So if you were trying to determine the thermal inertia at 4 in the afternoon, you would probably get it wrong if you didn't include the wind. But if you, what?
And then you would still get it wrong.
Right. But if you're trying to determine the thermal inertia at 5 in the morning, unless there was a really strong wind in the morning, which there pre-dawn, which there tends to not be, at that point, the effect of having, what I'm trying to say, the effect of having winds in the afternoon, that effect is relatively small in terms of the total temperature throughout the day. So the error at 5 in the morning by not including winds in the afternoon is probably relatively small. or at least you can fit the observed data throughout most of the day, except for that period in the late afternoon when it might be windy. So I think if you were trying to figure out was it windy in the late afternoon, it'd be a really cool thing to add to KRC. If you're trying to figure out what the thermal inertia is, I would say use 5 a.m. data, and maybe you don't have to worry about it. Now that's my opinion. Okay, so I would love to see it in there because I still think it'd be really interesting to understand the mini test results, the REMS results that Robin and Vicki are looking at.
Where's Vicki? I thought she was.
She's at a REMS meeting in Madrid this
Ah,
week. So
that's right.
REMS is this really cool instrument that looks out from MSL to an area about the size of this room. So it's not out of bed with what Themis might see. And it's acquiring surface temperatures every 15 minutes all day long, day after day. And they do see day-to-day variations that are probably due to the wind.
Mm.
But, so again, it depends on your problem. But if I'm trying to determine thermal inertia, I would say use 5 a.m. data and don't worry about the wind.
But on the other hand, just to make life complicated, I mean, the mapping that is done was done with test data. Got different answers in the mornings and the afternoons.
Right. That's another issue.
Another.
I'd like to put on, I would, if we're making a list of things we want to add, I'd love to add some wind capability to KRC. But try more to understand the microclimate of an area using infrared data, or the day-to-day variability using infrared data, than actually getting the thermal inertia right.
Yeah, Chris Haverly mentioned the name of someone, and it's escaping me right now, but he mentioned the other day that he knows someone who's working on mesoscale climate modeling patterns. So that sort of thing could be useful
Or it could be
for a
very
particular scene, for a particular scene. But it doesn't look like, as far as I know, I don't think any of the other thermal models include wind, with the exception of the
Vasavada.
Vasavada.
That's
Where
right.
they just have a constant 10 meter per second wind.
Yeah. Well, that raises the point I was going to make, and then we'll come to Robin. Another lesson I've learned in life, the hard way, and I actually never learned it, is a problem. That's why this is a sole authored paper, is ask your colleagues. Look in the literature. Before you spend a lot of your life's time building something, these days, look around, see if somebody else has got close, and ask them, collaborate. In this particular case, a simple thing to do now would be run KRC, call up Ashwin, say, would you please run your model with these 3 winds, speeds, and look at the results. And then you can decide whether or not to spend what's going to be a significant amount of time, I can almost assure you, trying to accommodate winds in a thermal model. Most of the models you see in the literature, somebody like me is behind them, and they've invested a good fraction of their life in getting to what appears to be a simple solution.
So
It takes a lot of time.
The thermal model that Ashwin has, isn't it derived from KRC?
Could be, because Dave Page was one of my students and Ash was one of his students.
Right. I mean, the tree of life sort of, Hugh Kiefer, as far as I know, myself, Joukowsky, Dave Page,
And who knows who else.
they all started with KRC. And so,
I'm having trouble just tracking all the different models from Page's group for LRO. Like, that's a message above itself.
so that's why, 10 years ago, I was this business of you're going to have models that what's the word I'm looking for? Not fork, but what's the opposite? Anyway, or not.
Diverge, propagate, split off.
There's a code term for code. Anyway,
Bifurcate is
But yeah, I think
technically
that model
binary.
has guts. KRC.
So it's our goal to have everybody come back to the one true church.
My
One model
question
is
is,
fine.
would anybody
Yes.
but me benefit from a 10-minute break?
Yes.
No.
Okay. On a totally unrelated note, the restrooms are out the door. Go down the hallway this way to the end, and then go that way.